Welcome to the video lectures for operating systems. In today's lecture, we will learn about storage structure, storage hierarchy, how a modern computer works, operating system operations, multi-programming and multitasking concepts, and dual mode operation of operating system. Let's move on to storage structure. So we know that a program, if it needs to be executed, both the code and data should reside in the main memory. So the main memory is a large storage media that the CPU can access directly. So it is also called as random access memory. It is volatile in nature, and the modern physical memory, that is main memory, is in the form of dynamic random access memory. We shortly call it as DRAM. The secondary storage device, it is extension of main memory that provides large non-volatile storage capacity. But the address range of secondary storage is not directly accessible by the CPU. So some examples of your secondary storage devices is hard disk drives. So it is rigid metal or glass platters covered with magnetic recording material. And the disk surface is logically divided into tracks which are subdivided into sectors. The disk controller determines the logical interaction between the device and the computer. So every device will have its own device controller and device driver. So the disk controller is very important. So non-volatile memory NVMe devices is also a secondary storage devices which are faster than hard disks. Various technologies have been implemented to further improve the storage capacity and the access time. So it is becoming popular as capacity and performance increases and price drops. Storage system organized as an hierarchy. So with respect to the corresponding terminologies with respect to speed, cost and volatility. So we are going to see the corresponding hierarchy in the next slide. The next mechanism associated with the storage hierarchy is caching. Very important, because if a particular data is requested for a program to be executed, it should be retrieved from the main memory. So the access time is very important. So the access time should be minimized so that CPU performance will be increasing. So the caching is one of the important aspects with respect to the improvement of the performance, where the copying of information into faster storage system. Okay, so main memory can be good as a cache for secondary storage. That is, from the secondary memory to the processor, we need to fetch the data for execution. So intermediately, your physical memory or main memory acts as a caching. So even though during the course of execution, other than the main memory, we are going to employ faster and small memory, which are called as cache memory, in between the processor and main memory, so as to improve further the performance. So as I mentioned in the previous slide, there is associated device driver for each device controller to manage the IO operations. So this will provide uniform interface between the controller and the kernel. The kernel or operating system should understand which type of device has been attached and what type of access mechanism with which the data transfer can take place between these two devices, processor and the device. So that is taken governance with respect to device driver. So this is the typical storage device hierarchy. So if you see here, so the closer, that is, these registers are associated with each CPU. So each CPU has its own register. So whenever a particular data is to be processed, the data should be retrieved from the secondary storage memory to the main memory, second storage device to the main memory, and then enter main memory to several levels of caches, and then to the register associated with the processor. So once the data comes into the register, the corresponding manipulation will take place. So if you see this layer, okay, so these magnetic tapes, optical disk, hard disk drives, non-volatile memory, all these are coming under secondary storage devices. Okay, these two, eventually optical disk and magnetic tapes, are tertiary storage devices. So all these four are having larger capacity, more number of data can be stored. But the retrieving of data from these devices is slow. The time required to retrieve the data from these devices is slow. So access time is slow. Next, if you see that main memory, it is closer to the processor. Okay, so but it is volatile in nature. All the remaining secondary storage devices are non-volatile in nature, and in between the CPU and the process main memory, we are having a cache memory. So here only one level has been shown in the diagram, but different levels of cache memory can be employed, okay, to improve further the performance. So as the closer to the processor, okay, so the access time is fast, okay, and the memory size, storage capacity is small. So as the distance from the processor to the storage device increases, okay, the storage capacity also increases, but the access time is slower. So this is about the storage device hierarchy. Now we will look on to how the modern computer works. So this typical architecture diagram is with respect to von Neumann architecture. So von Neumann architecture is where instruction and data is stored in a single memory. So instruction and data is stored in a single memory. You have a CPU, so single thread of execution of the programs, okay, associated with the cache memory here, okay. So there are n number of devices that can be controlled. So each and every device has its own device controller. Okay, then each device will interrupt the operating system. So there will be interrupt signal, there will be data signal. Okay, and then I/O request. Okay, so these are all the typical signals involved for I/O operation. So normal CPU execution, we have an instruction execution cycle and data movement. Okay, to one from the memory. Okay, so if in case the corresponding device, okay, needs to transfer the data through DMA, so that the data transfer can take place through DMA without the intervention of the processor. So the processor will not initiate the I/O. The DMA controller will take the control of memory cycle, and without the intervention of processor, the DMA controller will complete the I/O processes. So this is one typical facility we have, DMA control, in terms of direct memory access. So if you need to execute any instruction, the processor, if it needs to execute any instruction, the instruction and the data that is associated for executing should be should reside in the main memory, and it should be fetched from the memory. So that is the first cycle, the instruction fetch cycle, okay, in the course of instruction execution. So instruction will be fetched, okay, then the instruction will be decoded. Decoded means the processor understands what it should do for that instruction, and then execute cycle. So these three cycles are very important during the portion of any program execution. So this typical architecture is a von Neumann architecture, so where the instruction and data resides in a single memory. There is another typical kind of architecture known as Harvard architecture, in which there is a separate instruction memory and separate data memory. So what are all the operating system operations? So first of all, when you switch on the system, your PROM, programmable read-only memory, takes control. Okay, so and it first executes a program which is called as power on self-test. So it will initialize the basic system and it will check for all the corresponding units, function units are functioning correctly. So if is that correct, then the kernel is loaded. So the bootstrap program, simple code to initialize the system, load the kernel. So that is the functionality of bootstrap program. Then the kernel is loaded and the system daemons are started. So what are all the system daemons? It is the services provided outside of the kernel. Then always remember, operating system is interrupt driven. So the kernel is interrupt driven. Hardware interrupt by any of the devices can take place, and the software interrupt can take place using the cause of exception or trap. So usually the software error request for operating system service should be initiated through system calls. Okay, so these are all the important concepts with which the operating system operations are implemented. Now we are moving on to the multi-programming or batch system. Right? What is this multi-programming or batch system? Is single user cannot always keep CPU and I/O devices busy. So multiple programs, multi-programming organizes jobs, that is both code and data. So the CPU always has one to execute. That is, the meaning is n number of programs will be placed in the main memory. So So as I have defined, any program needs to be executed should be residing in memory. So if only one program is residing in the main memory, then there is no effective utilization of the CPU, right? So if n number of programs are available, the CPU can have one program at a particular time to execute. So the CPU will not be idle any particular point of time. So that is the concept of multi-programming. So several programs will be organized in the memory where that both code and data will be available. So the CPU will have at least one program always to execute. A subset of total jobs in system is kept in the main memory. So now there will be a concept called as scheduling, job scheduling, where that scheduler responsibility is to choose one among the n number of programs available in the main memory to the CPU for execution, right? So whenever the job has to wait, whenever the task has to wait for any IO or any other particular event, the corresponding operating system switches to the another job. So when operating system switches from one job to another job, the concept we call it as a context switching. So this is the logical multitasking is also called as time sharing, which is a logical extension of the batch system. So here the batch system there will be no much interaction between the user and the operating system during the course of execution. Now this is multitasking is going to be the logical extension of batch system. The CPU switches jobs here so frequently that user can interact with each job while it is running. The user also can interact with the job while it is executing. So this creates an interactive mode of computing. So here the response time comes into picture. Okay, so each and every user if they interact means the response should be within less than 1 millisecond or 1 nanosecond. So the response time is the important parameter with which multitasking operating system needs to be implemented. Okay, so each user should have at least one program executing in memory. If several jobs run ready to run at the same time, then there should be a CPU scheduling mechanism. Then if processes don't fit in the memory, swapping moves them in and out to run. That is, if a particular process has allocated some KB of memory locations, okay, but eventually the program size is too big, it cannot fit into the allocated memory. So there should be a swapping mechanism. So which are all the instructions that is currently in execution that will be within the main memory. Once that is executed, a new set of instructions will be fetched from the main memory, and this takes place, swapping takes place. Okay, so moving out of the code and moving in the corresponding instructions from the main memory. And the concept of virtual memory allows the execution of processes not completely main memory. This concept we will learn in detail in the memory management. So this is the typical memory layout of the program, the multi-programming system. You see, n number of processes are available in the main memory at a time, so the CPU can switch between these processes during the course of execution. Dual mode operation. So what is the need for dual mode operation? The operating system itself needs to protect itself from malfunctioning of user programs, right? So the dual mode operation allows operating system to protect itself and other system components. So there will be generally two modes of operation. One is called as user mode and another one is called as kernel mode. So how to identify the corresponding operating system is in the kernel mode or user mode. So it is mode bit. So the mode bit provided by the hardware distinguishes whether the system is in user mode or kernel mode. So it provides the ability to distinguish when the system is running user code or kernel code. So when the user is running, when the user code is running, the mode bit is user, that is it is in the 0. When kernel is running, the mode bit is in the kernel, that is 1. So it is 0 or 1. So if it is 0 in the user mode, if it is 1 it is in the kernel mode. Okay. So the system call changes mode to kernel, return from call resets it to the user. Okay, so whenever there is a request for any particular operation, okay, so every operation requested on behalf of the user is completed by the kernel. So this initiation of user operation, okay, is done by the system call. So the every user programs will initiate a system call. The system call will contact the kernel and the kernel will do the rest of the services on behalf of that system call and hand over the corresponding results to the user program. So this is how the operating system is itself protected from running the corresponding privileged instructions. Some instruction designated as privilege only executable in the kernel mode. Okay, the user program needs to initiate the respective system call for executing the privileged instruction which are executable only in the kernel mode. Okay, so why this system is being employed? Because to protect the operating system from malfunctioning codes. Okay, right? Because the entire hardware is a resources. That resources are controlled by the operating system. So the operating system acts as an intermediate between the user and the computer hardware, right? So whenever the user program we are writing, there will be some mistakes or errors. So those errors should not malfunction the hardware. Okay, so because of that, the operating system itself provides a facility through the set of system calls so that the privileged instructions will be executed by the kernel on behalf of the user process. So whenever the privileged instructions are executed, the corresponding operating system is in the kernel mode. Whenever the normal user code are executed, the operating system in the user mode. So here see, the transition occurs from the user process to the kernel. So if you see here, the user process is executing here. So it needs some services which can be provided by the kernel. So it initiates the system call. So now the mode bit is 0. So whenever the mode bit is 0, so as I said, the operating system moves to the corresponding kernel mode. Okay, so when mode bit is 0, it is in the kernel mode. When mode bit is 1, it is in the user mode. So it executes a system call on behalf of the user process and turns the mode bit 1 and returns the control to the user program. So in this way, the protection mechanism is implemented for the operating system. Thank you.